first paper is to Justin Boutilier, Zachary, Zhou, and Carla, Michini, and it's about shattering inequalities for learning optimal decision. Congratulations.
Thank you. Yes, it's time to talk. Okay, so this talk will be about shattering inequalities for learning optimal decision trees. This is joint work with my Justin J. Boutilier and my advisor Carla Michini. So this talk will be about decision trees. I'm sure many of you know what these are, but I'll go over them regardless. They're a supervised machine learning model used for classification and regression. We'll be focusing on the classification setting. So on the right is an example of a decision tree. You've probably seen something like this before. It's used to classify whether or not someone survived or died in the Titanic. And to interpret this, we start at the root of the tree, and we ask a series of yes/no questions until we end up at a leaf of the tree, at which point we make a classification. So as you can see, it's a very interpretable model, but the downside to using these models is the problem is generally hard to learn an optimal decision tree. And when I say optimal, I mean usually something like optimizing the number of misclassifications, so minimize that. Maybe plus like a regularization term, such as the number of branch nodes used in the tree. So to overcome this, it's common to use heuristics. So there have been heuristics like CARDS, ID3, and so on and so forth. They've existed for many decades. But inherently, heuristics sacrifice accuracy. So to overcome this, it's common to use ensemble methods, so multiple CART trees at once. But this sacrifices interpretability because there's many different trees floating around. So recently in the literature, there have been advances towards using exact methods and just saying the hardness is not a big deal. Let's use something like dynamic programming, static constraint programming, or Nib to learn these trees. And almost all of these works in the literature focus on univariate decision trees, where at each branch node, we only use a single feature of the data set. In this work, we'll be focusing on multivariate decision trees, where we use multiple features. So to clarify what this means, by using multiple features, we use a linear function of the features rather than just a single feature at a time. And you might ask, like, does this really make sense? Is this really, this is possibly sacrificing a lot of interpretability, right? Because when you have a single feature tested at every branch node, this is much easier to follow than just a linear function at every node. And this is this sort of a picture right here is an example of what happens when you look at this data set right here and you apply a univariate tree to it versus a multivariate tree. So with the multivariate branching rule, it just takes one rule to split the data points exactly, whereas you get this sort of a staircase pattern when you use a univariate tree. So I would actually argue that, it's arguable which one is more interpretable at the end of the day, but this is sort of a little bit of justification for why this problem might be interesting. So our contributions are a MIP formulation for the problem itself. And our second contribution, our big one, is the so-called shattering inequalities, which are a class of valid inequalities for the problem. And last, we'll show how to use these with within a Bender's like decomposition. So just to establish the notation, the data set is a set of points xi, yi, and the features are normalized to the 0-1 interval. There's p of them. And the classes are going to be 1 through k without less generality. And there are two hyperparameters that are of interest: the max depth and the regularization parameter alpha, the cost complexity pruning parameter. And the way the nodes are going to be laid out, it's going to be like a full binary tree. Every level is fully filled out, so to speak. And the depth is defined as the length of a path from the root node to the leaf node. So this is a picture here is a depth 2 tree. And this slide is all the decision variables. There's a lot of them. And the most important ones to look at are the W variables, the fourth one down. But I'm just going to go through all of them. So D sub T denotes whether or not we branch or prune at a given branch node. So this is a full tree, but we're not necessarily going to apply a split at all of them. If we don't use a branch node to split, we're simply just going to send all the data points down the left edge to, so for example, if 3 doesn't apply a split, meaning 3 prunes, we're just going to send every data point to node 6. So DT indicates whether or not we do this. ATBT, this is the branching hyperplane used at a given node. For each leaf node, we need to decide which class label we're going to associate with it. So we have these binary variables, sort of like a one-hot encoding sort of thing to indicate which class is associated with that leaf. I'm going to skip over DT real quick, and then ZIT. I guess I shouldn't skip over W. WIT is a binary indicator of where the data points end up. So WIT is one if and only if data point I ends up at node T. And ZIT is sort of this logical and of these two other things. But what ZIT really means in a sentence is it's one if and only if data point I sent to leaf node T, and it's also correctly classified there. So it's a bit of a mouthful. But WIT, I'm just going to say right now, it's the most important decision variable to be concerned with. In other formulations in the literature, so concretely, for example, the original Burt's paper, they have these sorts of variables, but they're only defined for the leaf nodes. And if you think about it, if you know that a data point has ended up at a given leaf, you can kind of tell which other branch nodes it ends up at, right? Because it's exactly all the branch nodes that are on the path upstream to the roots. But what I'm telling you right now is that you really want to have this sort of variable defined for all the branch nodes as well. So just to emphasize like what these variables actually mean, here's like sort of the decision tree structure. We have a node T, its left and right children are 2T and 2T plus 1. And at T, you have this branching hyperplane. That's the rule used to decide how points are sent down. And the red edges in this tree right now, these correspond to the path that a data point xi would actually take to go down to a leaf. And it arrives at node T. So we're going to say that WIT is equal to 1, but it goes to the right child 2T plus 1. So WI comma 2T, that is equal to 0. And let's say it arrives at this leaf node right here, it's corresponding, and it's classified correctly, its corresponding Z variable is equal to 1. So that's just what the variables themselves mean. So like I said, modeling W is the hardest part. It's that really is the hardest part. That's really what this whole work is concerned with, is just characterizing a set of acceptable routings of W. So we require two things of W. The first is a really easy thing to model, which is that these W variables, they're equal to 1 if and only if the ith data point, if that node lies on the path from the root to the leaf for the ith data point. So basically what this means is you need to make sure that for each I, there's exactly one of the WIT variables at the leaf that's equal to 1, sort of like a one-hot thing. So that's what constraint 1 means. And constraint 2 is sort of propagating this definition up to the branch nodes as well. That's the easy thing to model, but the second thing to model is that when you set these W values, that you're actually doing them in a sensible way. So if I look at a node T, a branch node, I have a set of points that are going left and a set of points that are going right. I really need to make sure that there's actually a hyperplane that can separate the two sets of points. Otherwise, this routing is just impossible to realize. So at this point in the presentation, I'm really going to lean on these colors, green and red, to kind of carry me through. And really, these are the 2 point sets that are being separated. So constraint 3, these are sort of like, I'm kind of hand waving this at the moment. Usually this sort of condition is realized using a big M constraints, but really what constraint 3 is saying is, does there exist a branching hyperplane in the set CalH, where CalH is defined as a set of all branching hyperplanes that can successfully separate these 2 point sets, the red and green sets. So CalH, if the definition is a little confusing, just omit the plus and minus 1. This plus 1 minus 1, and just make these inequalities strict. That's really that's sort of a up to scaling equivalent way of defining CalH. And I'm going to emphasize it's really just a set of hyperplanes that can realize this partitioning. And really constraint 3, what that is just, it's a non-emptiness test. I'm just testing whether or not A, B exists in the set CalH. If they do, these would be what I would return in the model. So this is the full net model regularization term, which is the number of branch nodes that are used. The term in parentheses in the objective, that's really just the 0 and loss for a given data point. Constraints 6 through 8, these are the constraints we just went over. Constraint 9 ensures that D is defined correctly. Constraint 10 ensures that every class, every leaf is corresponding to the class label. And constraints 11 and 12 sort of enforce this bitwise AND definition from Z. And that's about it. And modeling CalH is the difficult part. Most MIP formulations use big N constraints to do this, but as we all know, big N constraints are no good. So the question is there a way to characterize a set of acceptable routings without big N constraints? And the idea is that we're going to do this directly rather than indirectly using big N. And as part of doing this, we're going to end up omitting these branching variables A, B from the formulation. So this is just going to be a review of some, I guess, like statistical learning theory. Just going to go over like what does it mean to shatter a set of points. So we have a set CalC of which is a family of classifiers. So for example, the set of linear classifiers in the given feature space RP. And we say that a set of points in this space is shattered by CalC if for any assignment of binary labels, as in class labels to the points, there is a classifier in the family that can perfectly classify the set of points. And the VC dimension of CalC is a maximum number of points that can be shattered in CalC. So we're going to like part of this definition involves being nice about how you place the points and asking, can you shatter these points? And the fact is for linear classifiers, which are equivalent to our multivariate splits, the VC dimension is P+1. So to just go over this, we're just going to go over a simple example. We have two-dimensional space, and you can lay out 3 points such that it's always possible, no matter how the points are partitioned, to separate them. So this is to convince you that this is always possible. If you have 3 points, you can always separate them. I should be clear, you can be mean and you can put these 3 points in a line. They're all collinear, in which case the interior point can never be separated from the other 2 points. But part of this definition involves being nice and placing them in such a way you can do this. Now, if you have 4 points, it's you can convince yourself that it's going to be impossible, no matter how nice you are, how nice you lay out these points. There's always a configuration such that, or there's always a way to label the points such that the points are inseparable. So here's an example. In 2 dimensions, when you lay out 4 points in a plane, it's always going to be the case that either one point is perfectly enclosed within the others, it lies in their convex hole, or if this is not the case, the 4 points are the corners of the quadrilateral, in which case you can paint the points like this, and they're not able to be linearly separated. So this is just going over the little bit of VC theory. But how this applies to us is I'm really bad at explaining math, so I'm just gonna hope the colors and these pictures sort of explain what I'm talking about. Basically, the shattering inequalities are these inequalities right here. Basically, what we're saying with a single shattering inequality is that I have a set of points going left and a set of points going right at a branch node. And if they cannot be separated, for example, like this, then really all I'm saying is that if you send the points exactly as you prescribe using these red and green colors, then these points going left and these points going right, if you sum up the left-hand side variables, it would be exactly equal to this cardinality of the set I, where the set I is the number of points involved in this configuration right here. And so to prohibit this, I'm just going to say cardinality of I -1. So hopefully that makes sense. I'm not super great at explaining math, but that's the idea behind these shattering inequalities is we're generating this for every branch node. So at every branch node, this sort of inequality exists. And the set I is a set of points that can't be shattered. And lambda is sort of a labeling configuration. That's what the shattering inequalities are. And it's sufficient to only do this for minimal subsets. So even if you have like a large set of points that you cannot separate them, just pick a minimal subset of the points that cannot be shattered and define these inequalities. So this is what the Benders-like decomposition ends up looking like. The master problem is everything except for these CalH constraints. We just don't care about enforcing separability just yet. We solve it, we generate some, we determine whether or not the points can be separated in the manner prescribed. And if not, we add these shattering inequalities on the fly. So the question you should ask is, how do we actually find these shattering inequalities? So we're just going to review what IISs are, or irreducible and feasible subsystems. So if you think about it, at each branch node of the tree, there is a linear system that we care about. It's the one with the pretty colors. And basically, we're asking that given the prescribed routing, right? So W is going to be fixed. We ask whether or not we can actually send some points left and some points right. And the variables for this subsystem are the AT, BT corresponding to that branch node. Now, if this subsystem isn't feasible, What I claim is that each IIS corresponds to a minimal set I, which you can use to define a shattering inequality. And these IISs can be found efficiently, according to this paper right here. So to specialize this paper, like what they're doing to us, I'm just going to go over an example, or not an example, just this slide right here. If I have a set of points that just labeled in such a way with green and red, there's two cases that arise, and this is sort of a Farkas lemma like claim. Either I can actually separate them, like so this system right here is feasible, either this is feasible, or the two sets intersect, their convex holes intersect. This is believable, I think, right? If I have a set of points, I can either separate them or their convex holes intersect. And if their convex holes intersect, this is equivalent to saying that this polyhedron right here is non-empty, right? Because these Qs, what these are the sort of the convex hole multipliers. So basically what I'm saying is that I can combine the points going to the node 2t, and I can combine the points going to 2t plus 1 using these multipliers which sum to 1 and are non-negative. And right, these multipliers exist. That's really all I'm saying if this system right here is infeasible. And what I'm going to say, without really justifying it, is that every extreme point of this polyhedron directly corresponds to an IIS of the linear system here. Like they're equivalent. It's a one-to-one relation. Okay. So the experiments that we do is we look at 15 different data sets, and we compare against some other methods from the literature. And some of these methods from the literature only work on data sets that have binary features. So for these models specifically, we have to do an additional bucketization step. Just to clarify, our model doesn't require this because we work with numerical features, but for other models, this is required. We do the standard 75-25 train test split and tune a hyperparameter alpha. And this is all ran using for our models, we run this using Python and Ruby. And the code is available on my GitHub. The code base itself is kind of disorganized, but I think I'll clean it up at some point, hopefully. And there's two experiments that we do. One is what we call direct Nib comparison. We just compare against other Nib methods from the literature. All we're trying to do is just test the strength of the formulations. So our model is called SOCT. The S stands for shattering. And when we call it SOC full, that just means our formulation with big M constraints. I'm not really going to explain why we're adding these big M constraints back in. We're just claiming that our formulation, even if you define it using these big M constraints, it's still fairly strong. And we're comparing against OCT-H, which is the Burton Dunn formulation, and a FlowOct, which is by Guy and friends. And that's the FlowOct is a model that uses binary features, so we have to perform this bucketization step. And what we're looking at is just training and testing accuracy, solution times, and the relative gap. Since these are all MIT methods, we can find a relative gap and compare them for these models. And the second set of experiments we do is what we call a comprehensive comparison, where we compare against more methods from the literature and really try to establish which one is sort of the best as machine learning models. So some of the other methods that we do, one of the other methods that we test out is DL 8.5, which is an item set mining based approach. And for the OCT and OCT-H, which are by Burton and Dunn, for this we use the package that they provide with the interpretable AI, or that's sort of Burton's is like, I guess, like startup company or something like that. And they have these packages for their models. In these experiments, we do allow warm starts. We also do sort of an early stopping condition for our models, as well as FlowOct, which is we just terminate after 60 seconds if no new incumbent is found. It's sort of a practical thing to do. Again, this is really just to see which model performs the best overall in terms of as a machine learning model. So the trees that we get are not necessarily optimal, but anymore, but they still return fairly good trees, and we're just interested in seeing who overall does the best. So right, so these are the train accuracies. This is sort of sorted by data set. So I mean, everybody's sorted individually by data set. Like data set 0 is not just one data set for everybody. All of these lines are sort of monotonically increasing. And there's sort of a clear separation between the multivariate and the univariate models in terms of training accuracy. And this is fully expected simply because multivariate trees are better, or I mean, not better, but more expressive, I guess. But in terms of test accuracy, yeah, this divide is not as clear anymore. But I think multivariate models are still generally sort of near the top. And in terms of solution times, everybody's more or less the same for half the data sets, and then after a while, some multivariate data sets, I think our model in particular starts to take a little bit longer to solve. So that concludes my talk. Any questions?
Yes.
Yes.
Very nice talk, thank you. I had just a comment, I think, for your results. Since you see that the performance degrades when you move to test sets, right?
Sure, yeah.
I'm wondering if you try to just cross-validating and then picking for each method, you know, the parameters that were best. Like, you know, for some data sets, you may find that multivariates partitioning may not be so useful, and your approach can still work in that case, right?
Right.
And so then you would see maybe better test performance.
Yeah, so we did do tuning. It wasn't exactly like the cross validation. It's really just you know, partition the data sets like 50, 25, 25, and with that 25, just run once instead of doing like the multiple folds and just getting alpha that way.
Sorry.
So it's probably not as like good as doing an actual like cross validation, but it's one of those time constraint things.
Yeah, what
right?
I mean is like you know, choose the best model. So do parameter selection. Like, I'm not sure how to call it, but
like choosing alpha, right?
yeah, choosing should I prefer a multivariate model? How many parameters should it have, for example, versus a univariate one? And then, you know, choose that value, the value of that parameter that would give you the best performance on the validation set, right? And then evaluate indeed at the end for the best model for each approach on the test set.
To clarify by parameters, do you mean like the branching parameters like A and B, like determining like how many of those do we actually use?
Exactly.
Yeah, this is actually something I kind of admit. We actually, so you know how the birth and miss model, they have a binary variable for every feature as well, times every branch node. It's actually, we actually just don't do that. Like, we allow any branching hyperplane, like regardless of the number of features that we involve. So this is, I'll admit, this is sort of a weakness of our model. But
so there is no way to select like
the number of features used.
I see.
Yeah.
Interesting.
I argue that this is okay because it really cuts down on training time. But yeah, this is you correctly identified it. That is something we're not doing. We're not concerned with. The only sort of regularization we do in this manner is we control the number. We sort of control the number of branch nodes that are actually being used. So this regularization term right here, this is only for the number of branch nodes that are being used. And Burt's and Mrs. model does something where this D would also be indexed by the the features as well. So like it'd be D sub T comma J, where J is a feature, but we just don't do this.
Yeah, well, you could still here cross-validate with alpha, and you know, maybe because your model allows that more features in the linear like hyperplane thing, it may require like lower depth trees, right?
Sure,
so
yeah.
It may perform better with a larger alpha compared to someone else. So by tuning alpha,
right,
you could see better test case performance.
Sure, yeah.
This is what like a machine learning person would probably.
Right, yeah. Our tuning of alpha is not super sophisticated. It's really just something we just kind of do as a ritual, I guess, and then just pray for the best. Yeah.
You can also control the number of examples in each leaf node.
Yeah, that's true. Like a min sort of a constraint. Yeah, this is something that could be added as a constraint. We just don't do this.
If you want to control interpretability, so can you also fix the number of features used for?
I suppose you could, like, as in like instead of penalizing more features being used, actually like have a constraint that says just use it at most this much. I think we've thought about this, and it doesn't play super nicely with like the idea of the shattering inequalities because these just sort of assume all the features are there. I think we've I don't know. I think this is sort of a future work. It's just thinking about that, like, because constraining the number of features used at each node is it's a little easier to implement, I think, than just directly penalizing for each feature used. It goes in the objective. It's a little easier to do than that, I would say. But yeah. Yes.
How big are your training sets?
They're generally at most about 1,000 data points, which I'll admit is pretty low. It's sort of a general problem with these exact methods is how do they scale with bigger data sets, and 1,000 is pretty small in my opinion, but that's the most we do.
And how often did you actually prove optimality? You sort of skip past your gap very quickly.
Right. So for the direct Nib comparisons, this is without any warm starts and a 10-minute time limit. So yeah, I think
That's a really tough.
yeah, I guess I can't tell if it's optimized. I think it's roughly like a quarter to a half of them that were optimality was proved, but these were like trivial like cases. But yeah, for the other half, it's much harder to do. Yes.
Can you go to one of your final slides where you do the graphs?
These
Yeah,
graphs,
so I'm really confused with this because every line has a different x-axis. And so you're basically saying, right, 2 is the second best, or the second worst I did is at this level.
for a given data set.
Right.
Yeah.
So I really have no idea how to compare all these results.
Yeah, they're just
Right?
sort
I
of.
mean, if one is monotonically below the other, then it was better on all of them. But I have no idea how we.
Right.
compare.
It's yeah, that's true. It's I don't know. It was a.
It's a cactus one. Yeah. You could average the range.
I think in the paper we have like the averages and standard deviations. So for the direct Nib comparisons, we include this. I included this table over here, but I omitted it for the class. Yeah.
It's a cactus plot.
Cactus pot. Yeah, it's just being inverted.
This was Justin's contribution, not mine. So.
Okay.
Okay, let's thank the speaker again.